look at my
What? Oh no. Okay. Don't worry about the quiz. The only one I really care about. Sorry, I intentionally didn't put you on all of them because I didn't want you to log in and be like, oh, I've got 12 things to do. But I did want you to do that one. Give me just 2 seconds. And this, like, you're not going to find this hard. This is just a kind of what do you know thing. Give me 1 second. Edit assignment.
What's the audience versus
Assigned to all students. Okay, that should come your way now. It may take about a minute. Sorry about that. Okay, so okay. So, like we said yesterday, and where is my cheat sheet? Here we are. I did this last night, very late at night, so I'm very curious to see how that went.
How late?
I don't know, probably about 2:30 a.m.
Oh, wonderful.
It's fairly late. I woke up, so I thought I might as well make myself...
Early, but like...
Usually at night like that, I'd wake up and go for a little walk, but last night I said, I might as well make myself useful. So I made my chemistry note. So, yesterday we said that for some reaction, A becomes B, it reaches a state of chemical equilibrium. And we're going to introduce a new symbol here. This symbol here means equilibrium state. This is a reaction where the forward reaction occurs and the reverse reaction occurs. Now, not all reactions are equilibrium states. Some, I mean, if we're being highly precise, I suppose every reaction is an equilibrium state to some extent, but there are many reactions where, for all intents and purposes, the reverse reaction doesn't happen. If you blow up a stick of dynamite, it is highly unlikely that new dynamite is going to spontaneously form. It's a large, complicated molecule, right? And it just is essentially impossible for that to spontaneously form, and it is certainly impossible for that to spontaneously form in any meaningful quantity. Does that make sense? Carbon dioxide and water in the air, and the odd nitrogen gas, nitrogen dioxide in the air, are very unlikely to bump into each other and form a dynamite molecule. Does that make sense? So this symbol is reserved for reactions where the forward reaction actually occurs and the reverse reaction actually occurs. Does that make sense?
What is added to dynamite to make it explode?
Dynamite is a molecule, and all explosives are this, where it basically is a single molecule, it's actually more than just a molecule, but it's a molecule and then packed in surrounding molecules that basically provide fuel and oxygen right in close proximity to each other so that they are sort of self-combusting. Does that make sense? They don't need outside oxygen. They don't need atmospheric oxygen. They have everything they need right in there.
With atmospheric oxygen,
why is it that water puts out a fire if at hot enough temperature it can give...
Yeah, water will put out a low temperature fire, and it is the last thing you want to put on an extremely high temperature fire.
Just because it's two of the three...
Yeah, that's right. It is for water to effectively put out a fire, you have to have a very large volume of water relative to whatever the heat of the fire is, or it will make things worse, not better.
And with the grease fire,
and there's other things to be worried about. With a grease fire, for example, you can turn that into just an explosion, because now you're going to spontaneously, because a grease fire, the base of it, the grease itself, is hotter than the boiling point of water. You drop water into that, water becomes steam. Steam is has a much greater volume take up than air. So you put water into a grease fire, it turns to steam and just shoots the flaming grease everywhere. That's disastrously bad. And then decomposition can occur, which gives you oxygen. Yeah, no, bad. Do not do. Carbon dioxide, much better. But even just salt, baking soda, something like that, much better. Something just to smother it. A towel is flammable, so it's not your best choice, but still seriously better than some other things. You might be lucky enough to deprive it of oxygen before the towel burns up. You might not. But what you don't want to do is put water on. Absolutely. With a grease fire, your best defense is a lid, right? Like, as unscientific as that sounds, just putting a lid on it is going to deprive it of oxygen and go. If it's so violent that can't happen or you can't safely do that, smothering it with baking soda or with salt, but not flour. You don't want to use flammable things to put out a.
Fire extinguisher right next to our stove.
Yeah, I do too.
That's the best place.
But is there a difference between fire extinguishers or one you use for regular fires and one?
Yeah, they have different classes of them, but the ones that contain CO2 are always safe to use. They may not always be the most effective, like those ones that have powders and things that are meant to negate chemicals and things like that, but you're pretty much always safe off with the CO2 one, except to say that, again, with a grease fire, that you want to make sure that you're not just pumping a bunch of gas into it and spreading it out. So you want to do that from a distance. And
so what you're saying is, if I want to burn down a building for some random reason.
Anyway, we do need to get going. Sorry, but we said yesterday that if we tracked concentration versus time, you don't need to draw this. We said that the concentration of the reactant is going to go down like that and kind of work its way towards something, and the concentration of the product is going to go like that and work its way towards something, and eventually they should reach a steady state. Does that make sense? Do the concentrations have to end up being equal?
No, but they have to happen at the same rate.
That's right. So if we were to track instead the rate of the reaction over time, these, in fact, do have to meet in the middle. Does that make sense? And so if, say, this was the forward reaction, and it starts fast and kind of goes like that, and this is the reverse reaction, these will eventually end up being perfectly equal. Does that make sense?
I thought you said they don't touch.
Again, the concentrations do not need to touch. They could or could not, but they most likely will not. But if we're tracking rate versus time, the rates will eventually be equal to one another. Does that make sense? I know that can be kind of esoteric. That's sort of a particular distinction, but are we reasonably comfortable with that? Cool. And again, you don't need to worry about this. That's on yesterday's note. Am I actually streaming this amazing lesson? This exercise in clarity and conciseness? Okay, I gotta do better than bio. This one thing in bio was like the least focused thing ever. Okay. So now, just like yesterday, I want to look at some math, but let's look at a slightly more complicated example. Okay? Now, we're still going to go with something entirely first order. Okay? So for now, you're just going to trust me. Do you trust me? Yes, you trust me. This reaction is all first order. Okay? Do we got that out of the way? Great, we're out of the way. Okay. So in this case, we're going to look at a reaction. A and B react with one another to produce C and D. But both reactions happen. So the forward reaction happens, but also the reverse, in which case we say that we are in a state of equilibrium. And if we let this sit for a while, what would eventually happen?
The C and D reaction would simply start to happen, and then it would speed up, and it would slow down, and A and B would slowly speed up.
Yeah. And eventually what's going to happen? Where are we going to land? Yeah, you bet. Eventually we're going to land in a spot where they all seem to just hover. Does that make sense? Eventually the concentration of A, the concentration of B, the concentration of C, and the concentration of D will find a sweet spot where they just sit there. Does that make sense? They might be. I mean, you could design an equilibrium experiment so they all end up being exactly equal, but they don't have to be equal. Does that make sense? What they have to be is steady. They could be steadily the same, or they could be steadily different. That depends on a lot of things, but they'll be steady. And again, does that mean reactions have stopped happening?
No.
It just means that anytime A and B are being used up, they're also being made. And anytime C and D are being used up, they are also being made. Eventually, everything locks into a steady state. And we call that steady state an equilibrium state. And equilibria are characterized by appearing unmoving. They look like they're not changing. Now again, are they actually unchanging? No, they're changing, but they're changing. Yeah, or even more the point, they're changing equally. They are unchanging and changing at the same rate, right? Dischanging? Changing and also changing, but in the other way. I guess that's what I really mean. Okay, so for this, what would the rate equation be for the forward reaction? And I'm telling you that this is first order. Yeah, and I'm going to call it KF, but yeah, some constant.
Does the reverse always start at the bottom of the graph?
Assuming that you started with only reactant and no product, yes. But that's an assumption. Like you could start with equal concentrations of everything, and then they'd all start who knows where.
Times concentration of A times concentration of B.
Very good. And what would the rate of the reverse reaction be? I'm very fancy. What would the rate of the reverse be? Will it be some constant K?
Times concentration of C.
Yeah.
I don't know. It felt pretty hard.
Concentration of B would be, if the rates are equal, would they also be equal to zero?
Very good. And what we can say is at equilibrium,
The reason we're using RMAT.
sorry,
The reason we're using RMAT.
forward and reverse. So what can we say at equilibrium? The rates are equal. And to say the rates are equal, mathematically, how would I say that?
Rate at equals rate R.
I used lowercase, didn't I?
Yes.
And I'm going to put my math all in black pen so we can kind of distinguish it from just me talking.
You missed one bracket.
Oh no. Thank you for telling me.
Yeah, that one.
Okay. Could we mathematically go somewhere else with this?
Yeah.
What could I say next?
Well, you
Go
could
everywhere.
say KF,
Mhm.
AB equals R, KR CD, which is the same as what you've written previously.
Yep, very good.
It's just easier to notice.
Yeah, I like it. Very good. Oh, what am I doing? That was not good. Okay, I like that. Now, I don't know if you remember in grade 11 chemistry, and we had kind of a weird grade 11 chemistry experience. I don't know if I always covered everything the way I usually do, so you'll have to correct me. But when we did, for example, C1V1 equals C2V2, when we did dilutions, did I kind of have you sort of work your way to the equation? Do you remember, did I do that?
I believe so.
That's always something I like to do, where I kind of see if you can start at first principles and get there. So now we've taken two equations and turned them into one equation, which is good. But there's some things I don't like about this. First of all, it doesn't have one constant, it has... What's the point in having two constants? Could I turn this into one constant?
No.
Why not? Right? I mean, if that's constant and that's constant, can I put them in the same place?
It depends.
What's something I could do to put these constants in the same place? I like that. And it doesn't matter. Which one do you want to divide under? I want to get rid of...
I want to get rid of R. That's my
You have bias against R.
yeah, I do.
I want to put them on the left side as well. So I like that. Let's do that. So let's drop here and let's divide this side by KR so that it won't be here anymore. But of course, what I do to one side, I have to do to the other. But here's the thing. When I go to write my next line, I'm not going to write this as KF over KR because why bother? Since they're both constant, a constant divided by a constant is going to be a constant. They're different constants. You're right. If they were the same constant, it'd just divide to one. But they're different, and I don't know what they are. But I know that as long as we keep temperature and pressure constant, they will be constant. So what we're going to do is we're going to say this. Let's define a new constant.
Why did you go from fancy F to regular?
Why not?
There we go. And let's just say
You didn't change.
KEQ equals KF over KR.
Or care.
Or KR, it doesn't really matter. I can call it whatever I want, but does that make sense?
Well, what's the
I could call it, I'm not going to, because I don't want to, but I could. And I could say KEQ, and for whatever reason, for equilibrium constants, we use a capital K. There's not really anything meaningful about that. The thinking is just to help you know which type you're looking at. Does that make sense?
Would it be okay if we did the lowercase, but as long as we
Nope.
no?
Okay.
No, get in the habit. You know what I mean? If there's something that is kind of how things are done, get in the habit of doing it how it's done. And then this equation, there's nothing wrong with it, but I've got my constant on one side, and then I've got some variables on the left and some variables on the right. And instead of writing it that way, I want to write it so that I have a constant on one side and all the variables on the other side. How could I do that?
Divide
Very good. And so I could say the equilibrium expression for this equilibrium is that if we take the concentration of C and multiply it by the concentration of D, and then divide it by the concentration of A times the concentration of B, that is always going to be
Oh, this looks really familiar.
a constant.
I've seen this before.
This is,
Yeah, Q? Why did it go from a G to a Q?
it's a Q. That's a Q.
That's a Q.
That's a little cursive Q. Cursive Q,
That looks like
non-cursive Q. It's always been Q. It's not the droids you're looking for. All right. This is what we call an equilibrium expression. Now, that is the equilibrium expression when everything is first order. We'll talk. Don't worry. It's not going to be any harder. You just what are we going to have included? Exponents, right? But that's fine. Now, I want to note that you luckily did it how I wanted you to do it, which is nice, but we could have done it the other way and then flipped it. By convention. There's nothing magical about this. It doesn't have to be this way because of the way chemistry works, but just convention. What side of the road do we drive on?
Depends on where you live.
Here,
Well,
I drive
the
on
right side. We drive on the right. And is there something magical about right sides of roads versus left sides? No. In fact, there's countries where they drive on the left. You go to Japan, you go to Singapore, you go to
France.
England. No, France is on the right. Are there any
Really?
others, though?
Really? I think.
Yeah, France is on the right.
Oh, I thought French would be on the left because it's in
No, in fact, if you drive across the channel, if you will, you enter the channel driving on the right, and when you get to the other on the left, and then when you get to the other side, you have to drive on the right because you've left England and you've entered France, and they drive on different sides of the road.
How do you
Um,
safely make it so that you transfer?
I've never actually done it. I've always wanted to, but I've driven in both England and France, and I can confirm. England, left side of the road. Ireland, left side of the road. France, right side of the road. Both places, crazy people. They drive like friggin' maniacs.
Have the sidewalks got enough space. People are just.
But there's a convention. And the convention is just, again, nothing magical about it. But by convention, we do it this way, which is to say we put the products on
So,
the top and we put the reactants on. Now listen, look here. Would it be perfectly mathematically reasonable to flip this fraction and also flip that fraction?
Yeah.
Yeah, nothing wrong with it. The math would be fine. But in one of these let's all drive on the right side of the road kind of things, chemists have said, let's always put the products on top and the reactants on the bottom. Because in doing so, we're all going to be on the same page. We're all going to be doing the same thing. Does that make sense?
So it's just for convenience sake.
So by convention. And convention is important even if it's not intrinsic. Does that make sense? Because people are expecting it to be products on top and reactants on the bottom. So to make sure we write things in a way that people understand, we're always going to put our products on the top and our reactants on the bottom. Again, there's nothing magical about that. That is just the convention of how we do it. But we're going to do it. So let's make a little note. Note. Products over reactants. And don't worry, we're going to say this like 5 times more. So we're going to make a little note here, and then we will note it a few more times to make sure we don't forget. Now, this is, you could note things in letter writing convention, you mark things NB, which stands for note bene, which is Latin for note well. Sorry?
Do you not use the yellow one?
Do you not like the yellow one?
No.
Sure. Oh, it hit me. Is that one better?
Just a reminder, you have to beat up the paint.
No, it's good.
Are you still going to use it even when your foot doesn't hurt anymore? Just as a, like,
No. Oh my goodness, no, not at all.
That would be very
not like walking around with it, like pointing at the board.
Oh, you know what? Maybe it's my new pointer. I don't hate that. And maybe I'll work on some song and dance routines. And I can do the thing like, I need one of those like hooked ones so I can like, when people are talking too much, just pull them off stage.
Oh, no.
Really, you're right. It's got lots of
We should've
potential.
had one for the Christmas concert when my audio cut out.
You're telling me.
Yanked me.
Okay, now, this then is the convention, and now we're going to formalize it, and we're going to formalize it by describing what we call the law of mass action. Now, I'm not going to make you write this in words. The law of mass action says this. Who wants to read it? Go.
In a system at equilibrium, at a fixed temperature, the product of the equilibrium concentration of the product divided by the product of the concentrations of the reactants, each being raised to the coefficient of the substance in the equation.
Yep.
Must be equal to a constant.
Very good. That was well done. So you all know it now. We can just be done the lesson. I can give you the homework.
Yep.
Wow. Okay, I disagree. I think that's about as clear as mud. For sure. Yep. I think that's about as clear as mud. Maybe you feel great about it.
That was a terrible.
Can we turn that into a couple equations? A chemical equation, then a math equation?
Yeah.
Okay, let's talk about that. Now, what that means is this. If we have some coefficient of thing A, maybe it's 2, maybe it's 3, and then we've got some coefficient of B, and it's in an equilibrium state with the first product, which is some amount of C, and it's also got, you asked me not to use the yellow. Oh, shoot. What do we like? Ooh, how about purple? Purple is good. And something D. By the way, we are showing this as 2 and 2 things. This is generalizable to as many things as you have. If it was 8 reactants, you can write out 8 reactants. If it was 11 products, you could write out 11 products.
So no matter how many products or reactants you can use this.
That's right. This does not matter. This is a fully general equation. What we can say is this. Everything is going to be equal to some constant. And by convention, we use KEQ. You will sometimes see textbooks and sources use KC. Or sometimes they will even use it really specifically. For example, if you're talking about an acid, they might call it Ka for acid. If you're talking about a base, they might call it Kb. If you're talking about a solubility, they might put SP for solubility potential. They will mess that subscript around depending on how, you know what I mean, just as an identifier.
Or should mean setting.
Does that make sense? So they will do with that lowercase subscript whatever they want, whatever's going to kind of help identify it, which is why we're a little bit strict about using capital K's here, because we kind of understand that when you see a capital K, we're talking equilibrium. Does that make sense? Cool. So let's read this sentence and try to make something of it, shall we? Okay.
One sentence.
The product of the equilibrium concentration of the products. So first of all, when we say the product in math, what do we mean by that? We're taking the product if we take two numbers and
Looking back.
multiply them. Good. Okay. So this means we are multiplying. And we said on the top, the concentrations of the chemical products. Good. So we use the word products in two different ways. Don't you love that? Yay, English. So, note, we've already seen this, right? What did we do here? We multiplied the concentrations of the... What are we going to do here? We're going to multiply the concentrations of the products, which means we're going to multiply the concentration of C by the concentration of D. But, note here, and you guys are going to want to yell at me, I bet. Maybe not. I mean, maybe you always do.
I don't understand. What is EQ?
Equilibrium.
Oh. Like every time you do. Why Q?
So now, let's note here.
Q.
What's that say?
Take the
Being raised to the coefficient of the substance.
What's it mean to be raised in math?
like exponent of your
Exponent. Which means that in this law, the coefficient acts as the exponent. Now, that means whatever number here is going to work as an exponent there. Whatever number here is going to work as an exponent there. Wait a minute, what did I tell you in rate laws? Didn't I tell you in rate laws that we couldn't do that thing?
yeah, because the amount of moles. Or would these be the amount of moles, the coefficients?
Yes,
Okay, yeah, you can.
but we have to. And I'm going to explain why. And I'm going to explain why it's not a And I'm going to explain why it's not a contradiction. And I've actually decided you're right. That's exactly right. And I've actually decided I'm never going to teach this in quite the same order again. The other week I was in here working away and doing some math and coming up with a new way I want to approach this. But the reason for it is this. It seems paradoxical that the coefficients from the balanced chemical equation are the exponents in this equation when they're not necessarily the exponents in the rate equations. But here's the difference. Here's why. I'm going to show you what I was working on last week, and maybe you can see it. Is this the one where I got going? Yeah, this is the one. Where for this reaction, there is a chemical reaction where if you take nitrogen dioxide and react it with carbon monoxide, you can get nitrogen monoxide and carbon dioxide. Does that make sense?
No. How would on the bottom half?
Look at the reaction. It makes sense. Don't worry about any of this right now. Just look at that. That's your chemical equation. Does it make sense? Basically, they swap an oxygen. Nitrogen dioxide gives an oxygen to carbon monoxide and turns into carbon dioxide. Can you see that? Now, here's the thing. It actually is true. It actually is true that any equation where we do a rate, it actually is as easy as taking the exponents from this equation and putting them in there. Only I told you it wasn't. And the reason I told you it wasn't is because this reaction doesn't actually happen like this. You would think it happens like this. But it's actually zero order for CO because this isn't the reaction shown step by step. It's the overall reaction. In the real step, scientists actually discovered that this reaction has to happen in two steps. First, an NO2 has to bump into an NO2. And they turn into an NO3 and an NO. So the carbon monoxide doesn't turn the NO2 into an NO. Carbon monoxide never actually bumps into NO2. Does that make sense? First, two NO2s have to collide. And the equation of this would be rate equals K and then NO2. And how many of them are there? Two. So it's second order. That's that reaction. And this is the slow reaction. This is the one that takes a long time. So when we figure out the speed of the reaction, we would have found that it was 0 order for CO and 2nd order for NO2. And to us, we would have said, oh, so you can't trust the coefficients. But you can trust the coefficients. What it means is there's actually 2 reactions that have to happen. This first one, which depends on an NO2 bumping into an NO2, which is 2nd order, because 2 things have to bump into each other. And then this other reaction here, rate equals K. This would be a different rate, K. And what are the 2 concentrations here? NO3 and CO. But the thing of it is, this reaction is so fast that we don't have to care about it. It just takes care of itself. Does it make sense? So when we worry about the rate, you have to worry about the slowest person. It's like this. If we were going to hike through the desert, we wouldn't have to worry about who in here is the fastest desert hiker. That's not going to determine how long it takes us to get across the desert. We would have to worry about who is the
slowest.
Would you like to know who I think that is?
Who's dragging themselves across the sand, complaining that they don't have enough water.
Correct. So I'll say this. I think I've got camel-like tendencies.
What?
I'm assuming this is just big water storage and that I'd be fine. This is what I think. I think I'd get through that desert just fine.
Water, I need water.
This is what I'm saying. So anyway, so I don't want to get into this too much. If you're curious, if you want to know why this works, I can show you here that when you get to equilibrium, you have to actually deal with all of the reactions. The forward reaction of this, the backwards reaction of this, the forward reaction of this, and the backwards reaction of that. Whereas, when all you're figuring out is how fast a reaction starts off, what we did last unit, just like us crossing the desert, you only really need to worry about what's the slowest part of this whole thing.
Would we be able to determine the coefficients if you gave us one of those charts for this equation, or would we?
So if even last unit, first of all, yes. And this is actually how scientists figure out when a reaction takes more than one step. If they do what we did last unit, and the coefficients don't match the equation, they know it must be a multi-step equation. They know one thing must be happening, then another thing. They know it must be at least 2 steps. And then they can actually mess around with the equations, and they can actually work out step by step how a reaction happens. That is really cool stuff, but it's beyond the scope of this course.
Do they do that experimentally, just writing it out?
That's right. So I hope that cleared that up a bit. And listen, look here. If everything I just said makes no sense to you, you have 2 options. 1, come talk to me. I would love to talk through it with you and see if we can help it stick. If you're the type of person who is like, I really need to understand why something works, and that was too quick for you, come talk to me. We'll get you there. If you already got it, great. If you're someone who's like, couldn't care less how this works, just tell me what to do, cool. Ready? When you do rates, you have to figure out the exponents by looking at the data. When you do equilibria, what are the exponents? Coefficients. Whatever the coefficient is, that's the exponent. Which means equilibria are actually easier than rates, and they are. Getting this equation, just look at the balanced chemical equation, put your products on top, put your reactants on the bottom. Where do the exponents come from? You got it. Good. Hey, let's get some practice with that. Write an equilibrium expression for this guy. Why did I put nothing in subscripts? Don't know, couldn't tell you.
Well, at least you spaced the coefficient. Well, I guess.
Let's not give me credit, that sucks.
Well, you deserve some credit.
Also, can we talk about this garbage equilibrium system?
Is there really no equilibrium sign in Unicode?
There is actually. In fact, when you get to the homework that I made myself, you will see I used it regularly. Versus this example that I shamelessly stole from a note that I made years ago before I don't even know if I made this. This I probably, at some point I stole this from someone. Anyway, it sucks. I think your hat looks very nice. Get to work. I want an equilibrium equation for this. You tell him, Chris. Also, write an equilibrium expression. Yeah, next time I teach this course, I'm going to do it in a different order. Decide I'm going to stop just waving my magic wand over this lesson and being like, just trust me, it works.
Do you know that you're more on the ball than Mr. Calford?
I find that hard to believe.
We got our tests back from you, the mark, like 4 hours later. Mr. Calford hasn't marked me.
He also had to do the math homework thing from 7 to 10.
Yeah, and more to the point, like, don't play mom against dad. Don't do that. Like, listen.
Oh, I've done that before. It's not end well.
Everyone does things differently, and I happen to be a believer that I like people getting their work back right away. But I'll also say you guys gave me a great gift, which was everyone was here and you all wrote it, and that's like manna from heaven to me. Oh, when I saw that, everyone was here. I had the whole class set. I think it has been. Can I tell you something? I think that was the first time in 6 years that I've given a test out and the entire class has written it all at once. And then you guys did really well. I was elated. It made my night. I was like, oh. I was like dancing. Da da da. Overture, curtain light. This is it. Sorry? It was worth it. I'd dance again. Talk to me, crew. What's our equilibrium equation here? Yeah, Jonesy, what do you got?
KEQ equals CO2 gas power 4 times H2O gas power 2 divided by C2H2 gas to power 2 and O2 to power 5.
Very good. And I want to note something again where we said we're using the square brackets that we always use for concentration, but given that these are gases, would we use concentrations? We would just use moles, number of moles. And that's okay. That's going to work. We're happy with gases. We're happy with solutions. Where does it get messy? Solids. Solids are the enemy. Or even liquids. Solids and liquids are the enemy. Aqueous solutions are great. Gases are great. Because in that we assume even spread of everything. Whereas if you think liquids, they might be two separate layers, right? Think like oil and vinegar, right? They're non-miscible with one another.
I just seen something about that. It was like, so oil floats on water, so that means you just put some oil in your feet and you can walk on water.
I don't think the buoyancy would support your weight.
You didn't put your. You always get so mad when we don't use like
You would
the
float.
freaking gas.
Whoa, wow. Okay. All right.
I'm lighter than Will, right?
Will's longer.
Will's longer. It's a density question. It's not mass. It is density. That's fair.
And gingers are dense.
Wow.
If my hair is dense, does that mean it dries quicker or doesn't get wet as fast?
I don't know.
I
I don't have a good answer to that question. Okay. Well done. Now listen. Listen. In the next question, we're going to see what we can do with this. And what we can do with this is this.
Is this?
That was quite a sentence. At equilibrium.
Highlight C2H2.
Sorry?
Highlight CH2 pink.
I think I did, and I think you should try to pay closer attention. So
Why do you point
Play
with the
closer
handle
attention.
instead of pointing with the tip?
I kind of like it.
You should be holding it by the handle and pointing. Yeah, like that.
I gotta be honest, I can't tell you why, but that feels better. It just does. The balance is nicer. Anyway, and I also like if I need to. I'm ready. I should, you know what, that kind of felt like it was coming off. And I thought I was in real danger of pulling a full Calford there. So I'm just gonna be careful. Orlando hit me with his cane. Anyway, which, the nice thing about that is there's so much subtext. Like, why did he have a cane? Anyway.
I'm glad you're recording this.
I know, me too.
Yeah.
So here we go. At equilibrium, when
That feels like exactly like how I would say it.
when the reaction reaches equilibrium, this equation will be true. And only when the reaction reaches equilibrium. So if the concentrations are still changing, is the reaction at equilibrium yet? No. So if you want to learn the equilibrium constant of an equation, of a reaction, no problem. Put everything into the solution. Wait until it reaches that steady state. Wait until it reaches equilibrium. Then just do this equation and you can solve for the equilibrium constant of that equation. Does that make sense? We kind of okay with that? Cool. We're going to do that before we leave. That'll be where we leave off today.
We have only one highlight.
Probably because you steal the rest of them.
Okay? Okay. Now we're going to do this question. Okay. So you'll be quiet. Okay, so here I want to write an equilibrium expression again. Who can give it to me?
Sorry, I couldn't hear you.
Q equals PCl3 plus CO2.
Plus?
No, sorry, CO2.
Do I need exponents here?
No.
How do you know that there aren't any?
Because no, the exponents are 1 because there's nothing else.
Good, yeah, we take them from the
You put something
coefficients
to the
here.
power of 1, it's still
That's right. So if you want to put a 1 there, you can. Nothing wrong with that. Or we can leave them blank. Very good. What should go on the bottom of this? Yeah, that's good.
Where I'm going to draw.
Okay, now, once we reach equilibrium, we can put the values we have into this equation and we can actually solve for the equilibrium.
Can you talk louder,
No,
please?
no, this is it. This is what we're doing. So this isn't a bit. We're trying something here. We're trying something. At equilibrium, we know the concentrations. Yeah, Ryan, what's up?
I have a question, but I feel like the why question is pretty hard.
I'm not gonna lie, I didn't hear a word of that. But I'm gonna assume it was a compliment, and I'm gonna say you're welcome.
Yeah, I feel bad for Ryan. He probably can't
Can
hear
you
you.
stop writing a cursive Q if you're not going to write a cursive E?
No, I'm good. So at equilibrium, because one of the things a term we use to describe those is chemical species. I don't know why.
I hope you know you're slowly getting louder and louder.
So we can solve for KEQ. Now, you need to take the temperature into account because we know that the rate of a reaction is influenced by its temperature and pressure. So we need to know that if the temperature changes, KEQ is going to change. It depends on a lot of different things. But a KEQ value is only true for a specific temperature and pressure. So they are very specific, which is why we're always using, or most often using, SATP, standard atmospheric temperature and pressure. 10 comedy points. All right, so I'd like you to solve for KEQ, please. That was really funny. I like that. He said, "Don't you start raising your voice with me."
What is in between the RX and Celsius? What is that?
What?
What is that?
Is it like the add symbol or is that a W?
That's your at symbol? Oh, that is sad.
I think it looks pretty good.
I like it right at.
What if like a W and then it's an A? And
It's an A. That's an A.
there's not an A. You want like a W.
Dude, you're actually
Do it
getting
bigger.
ready to whisper. That's pretty funny.
Because they think it's a bit.
It's not a
It's
bit.
just Orlando getting mad at people being so loud that he's trying to.
I'm not your dad.
No factory over. I'm not your dancing monkey. Got it.
No facts.
It's my favorite equation. All right, come on. I want this solved.
I don't think it was over. I think it was underlined.
No, that was a fraction.
What was your exclamation part?
Factorial.
It's factorial, really?
Yes.
How do you know factorial?
Aren't you the one who did
I
it
have
yourself
the
when you
answer.
wrote no on the board? I remember somebody saying no factorial.
Everyone said no factorial.
Is it just smaller?
You tell me? So what should I do here?
I hope you know you're gonna go home and you're gonna start talking like that.
0.2.
I'm very quiet when I get home. After whole days of being loud at school, some days I go home and I don't speak at all. I just don't talk because I don't want to, because not that I like talking here, but it gets exhausting. Like, it's just, you're on all day. So yeah, sometimes I go home and just don't speak to anybody.
What's wrong with your battery? That's like a heart over it and it's been going down even though it's plugged in.
Yeah, that's because this is a slow charge just from my dock, and I've just got lots going on my computer right now. So yeah, it's just telling me that.
Or not have lots going on in your computer.
Oh, no, sorry, smart charging, that's something different. Windows 11 now gives you an option to not take the battery all up to 100%, because you get longer battery life if you sort of leave it running typically between like 30 and 80% in most of your cycles. There you go. All right, what do I do?
Actually, Jonesy was gonna do it.
Jonesy, go.
I'll let him do it.
No, you do it. I feel like
Oh, okay, fine. So,
You guys are so agreeable.
the concentration of ECl3.
Yeah, which is?
24 molar,
What is it?
0.25 molar,
Okay.
and then
The math teacher in me cringes a little at 0.25, but that's fine. No, that's good. Good. We're cool.
And then
0.25, really?
use the concentration of chlorine gas at 0.25.
There we go.
There you go.
You could say 25 100ths if you're feeling fancy.
Well,
a quarter,
okay,
a quarter.
Why do you cringe at that?
on the bottom, you take the concentration of PCl5, which is 0.15.
Excellent. Very good.
And that should just come out to
Okay, so first things first, what's our unit going to be in the product?
molar.
Yeah, because that'll cancel with that. And we're back to this thing where the units are going to be different for each equation. It just depends on all kinds of things.
Wouldn't exponents mess that up?
Oh, boy. Yeah.
Do you want the number?
Yes.
0.416 repeated.
Oh, that's not where I was going. Cool. And how many sig figs do we have?
3.
Mm, it's, oh, darn right it would. So 0.42 molar.
Show me.
All right.
Round up, yeah.
And so now we know the equilibrium constant for this reaction, but only at,
We don't have that much
Standard.
to go under more.
in this, that's okay. I mean, you could even put it over here if you felt so inclined, or just, I mean, it's in there, but I just kind of like the idea of having it written by itself. And the thing of it is this, that will now be true for any concentrations you start with. They will find themselves to a place where the concentration of this times the concentration of that divided by that will equal that
At that temperature.
at that temperature. But there's all kinds of different combinations. You could start off with tons of this, tons of that, only a tiny bit of that. It's going to find its way to this being the ratio. You could make this really big and this really big and that really small, and they'll find a totally different equilibrium. But that totally different equilibrium will still equal this. There's an infinite number of combinations of these that will equal that. So there's lots of different possible equilibria, depending on your starting conditions. But as long as you keep the temperature at that and keep the pressure constant, which I didn't even mention in this question, though I should have, you will get that as your product, which is pretty cool. That's how equilibria work. Tomorrow, we will then take that and apply it to saying, okay, why is this useful? What does it tell us? But I hope even just looking at this, you start thinking about what are ways could I manipulate the fact that I know that this ratio will always have to be a constant to get the outcome I want. This relates back to how we knew when we did our esters lab that we had to use a strong acid and that we had to heat the reaction vessel because we can manipulate KEQ and we can manipulate concentrations to make sure we get the outcome that we're looking for more. We can favor one side of the equilibrium over another. Does that roughly make sense? Listen, I'm not going to give you any homework per se until we finish the note tomorrow. But if you wanted to start your homework by doing the A part of each question, because for each of these things I gave you in the homework, the A part is just to write an equilibrium expression. Well, could you do that? Yeah, you bet you could. So that would be great homework for tonight, just to make sure you're comfortable with that. Does that make sense? All right, you guys are doing great with this. I don't know if I said that after your last test,